Hey everyone, welcome back to STEM Education with Olufemi, your go-to channel for simplifying complex science and technology topics. Today, we're diving deep into the world of capacitors, those little components you find in almost every electronic device. We'll cover everything from the basics to the latest advancements, so whether you're a student or just curious, you're in the right place. Capacitors are absolutely crucial in modern technology, from the smartphone in your pocket to electric vehicles and renewable energy systems. They're the unsung heroes that make our digital world possible. A capacitor is a passive electronic component that stores electrical energy in an electric field. Unlike active components, it doesn't generate energy, but rather stores it for later use. Every capacitor consists of two main components: two conductors called plates or electrodes, and an insulating material called a dielectric that separates them. Here we see a basic capacitor structure. The two blue rectangles represent the conducting plates, and the space between them contains the dielectric material that prevents current from flowing directly between the plates. When voltage is applied, positive charges accumulate on one plate while negative charges accumulate on the other. This creates an electric field between the plates, shown by these yellow arrows pointing from positive to negative. This diagram shows how molecules in the dielectric material become polarized when placed between charged plates. The electric field lines demonstrate the energy storage mechanism that makes capacitors so useful in electronic circuits. In circuit diagrams, capacitors are represented by two parallel lines with a small gap between them, symbolizing the two plates separated by the dielectric material. In summary, capacitors are fundamental components that store electrical energy by creating electric fields between conducting plates separated by insulating materials. Capacitance is a fundamental property that determines how much electric charge a capacitor can store. Understanding this concept is crucial for working with electronic circuits. Capacitance represents how effectively a capacitor can accumulate and hold electrical charge when voltage is applied across its terminals. The capacitance value is calculated using a simple but powerful formula that relates charge, voltage, and capacitance. The formula C equals Q divided by V shows that capacitance is the ratio of stored charge to applied voltage. This relationship is fundamental to understanding how capacitors behave in circuits. Capacitance is measured in farads, but practical capacitors typically use much smaller units like microfarads, nanofarads, and picofarads. Here we can see the relationship between different capacitance units. A farad is actually a very large unit, so most practical capacitors are measured in microfarads, nanofarads, or picofarads. To better understand capacitance in action, let's examine how a capacitor charges over time when voltage is applied. These graphs show how voltage and current change as a capacitor charges. The voltage rises exponentially toward the supply voltage, while the current starts high and decreases as the capacitor fills with charge. The capacitance value directly affects how quickly this process occurs. Remember, capacitance is fundamentally about the relationship between charge and voltage. Higher capacitance means more charge can be stored at the same voltage, making the capacitor more effective at energy storage. Now let's explore exactly how capacitors work. Understanding this process is crucial for grasping their role in electronic circuits. When we connect a capacitor to a voltage source, something fascinating happens. Let's start with a simple circuit containing a capacitor and a battery. When voltage is applied across the capacitor, electrons begin to flow in the external circuit. This creates an imbalance of charge on the capacitor plates. Electrons flow from the negative terminal of the battery toward one plate of the capacitor. This plate accumulates negative charge as it gains electrons. Meanwhile, the other plate loses electrons to the positive terminal of the battery, leaving it with a positive charge. This creates an electric field between the plates. This diagram shows the complete charging process. Notice how electrons accumulate on one plate while the other plate becomes positively charged due to electron deficiency. The dielectric material between the plates plays a crucial role. It acts as an insulator, preventing the accumulated charges from flowing directly between the plates. This comparison table shows the key differences between dielectrics and capacitors. The dielectric is the insulating material, while the capacitor is the complete component that stores energy. Let's define three important terms. First, the dielectric is the insulating material between the capacitor plates, such as ceramic, plastic film, or paper. The voltage rating is the maximum voltage that can be safely applied to the capacitor without damaging it. Exceeding this rating can cause the dielectric to break down. ESR stands for equivalent series resistance. This represents the internal resistance of the capacitor, which affects its performance in alternating current circuits. This specification table shows how different capacitor values relate to voltage ratings and other important parameters. These specifications help engineers select the right capacitor for their applications. The electric field created between the charged plates is where the capacitor stores its energy. This field is maintained by the dielectric, allowing the capacitor to hold charge until it's needed in the circuit. Capacitors come in various types, each designed for specific applications, voltage ranges, and performance requirements. Understanding these different types helps engineers choose the right capacitor for their circuits. Each capacitor type offers different advantages in terms of size, capacitance values, voltage handling, and frequency response. Let's explore the most common types used in electronic circuits today. First, we have ceramic capacitors, the most common type found in electronic circuits. These small, inexpensive components are non-polarized, meaning they can be connected in either direction. Electrolytic capacitors offer much higher capacitance values, but are polarized, meaning they must be connected with correct polarity. They're commonly used in power supply circuits for filtering and energy storage. Film capacitors use thin plastic films as dielectric material. They offer excellent stability, low loss characteristics, and are non-polarized. These make them ideal for audio circuits and precision applications. Supercapacitors, also called ultracapacitors, can store enormous amounts of energy and charge or discharge very quickly. They're increasingly used in electric vehicles, backup power systems, and energy harvesting applications. Finally, variable capacitors allow you to adjust their capacitance value mechanically. These are commonly found in radio tuning circuits and trimmer applications, where precise capacitance adjustment is needed. Each capacitor type serves specific purposes in electronic circuits. Choosing the right type depends on your application's requirements for capacitance value, size, frequency response, and voltage rating. Capacitors have numerous practical applications across many industries and devices. Let's explore the key ways capacitors are used in modern technology. First, energy storage. Capacitors can store electrical energy and release it very quickly when needed. A perfect example is camera flashes, where capacitors store energy from the battery and then discharge it rapidly to create a bright flash of light. Power supply filtering is another crucial application. Capacitors smooth out voltage fluctuations in power supplies, converting rough alternating current into stable direct current. This filtering removes noise and provides clean power to electronic circuits. In signal processing and audio equipment, capacitors act as coupling and decoupling components. They connect different circuit stages while blocking unwanted DC signals, and they filter out noise to maintain signal quality. Motor starting is a specialized application where capacitors provide the initial boost of energy needed to start electric motors. Start capacitors give motors the extra torque needed to overcome inertia, while run capacitors improve efficiency during operation. Power factor correction improves the efficiency of electrical systems. Capacitors compensate for inductive loads, reducing reactive power and improving the power factor. This results in more efficient power transmission and lower electricity costs. In automotive applications, capacitors play crucial roles in energy recuperation systems, especially in electric and hybrid vehicles. They store energy from regenerative braking and provide power for various electronic systems throughout the vehicle. Capacitors are found everywhere in modern electronics, from the tiny capacitors in smartphone circuits that manage power and filter signals to large capacitors in power supplies and industrial equipment. Every electronic device relies on capacitors for proper operation. The capacitor industry is experiencing rapid transformation driven by emerging technologies and growing market demands. let's explore the key developments shaping the future of capacitor technology. Market growth in the capacitor industry is being driven by the explosive demand for electronic devices and renewable energy systems. The global capacitor market is projected to reach $80 billion by 2033, growing at a compound annual growth rate of 6%. Miniaturization is a critical trend as manufacturers develop smaller, more compact capacitors for portable devices and high-density circuits. Modern capacitors must deliver the same performance in increasingly smaller packages. High-frequency applications are driving demand for specialized capacitors with excellent performance characteristics. These are essential for 5G networks, Internet of Things devices, and advanced communication systems where signal integrity is critical. Electric vehicles represent a major growth driver for the capacitor industry. These applications require capacitors that can operate in harsh environments with extreme temperatures, vibrations, and electrical stress. Advanced materials like graphene and organic polymers are revolutionizing capacitor performance. Supercapacitors are emerging as efficient energy storage solutions, offering rapid charging and long cycle life for various applications. Modern circuit designs are incorporating improved capacitor technologies to enhance performance and efficiency. Low equivalent series resistance capacitors minimize energy loss and heat generation, making them ideal for high-frequency applications. These developments position capacitors at the forefront of technological advancement. From enabling next-generation electronics to supporting sustainable energy systems, capacitors continue to evolve to meet the demands of our increasingly connected world. We've covered a lot of ground in our exploration of capacitors. These remarkable components are truly the unsung heroes of modern electronics. Let's quickly recap the key points. Capacitors store electrical energy and release it when needed. They come in multiple types, each designed for specific applications. They're essential components found in virtually every electronic device we use daily. The capacitor market is growing rapidly, driven by innovations in electric vehicles, renewable energy, and advanced electronics. The future holds exciting possibilities with supercapacitors, flexible designs, and new materials. From smartphones to electric vehicles, from renewable energy systems to space exploration, capacitors are the silent enablers of technological progress. Thank you so much for joining me on this journey through the fascinating world of capacitors. I hope you found this exploration both educational and inspiring. If you found this video helpful, please give it a thumbs up and subscribe to STEM Education with Olufemi for more exciting content on science and technology. This is STEM Education with Olufemi, making complex science simple and accessible for everyone. Until next time, keep exploring and stay curious.